Hello everyone. In this video, I want to show you a really interesting way to look at a lot of things in math called the hierarchy of operations. My high school pre-calculus teacher, Steve Weisberg, emphasized this idea, but I haven't seen much about it elsewhere. Thus, I'd like to share it with you. Just a quick note, I will only be using high school level math in this video before calculus. Also, keep in mind that I won't emphasize rigor or proofs in my explanation. The emphasis is on the concepts and ideas. Anyway, let's get into the video. What is multiplication? Of course, it is just repeated addition. Let us place these two operations in a table that shall be called the hierarchy of operations. In the same fashion, exponentiation is simply repeated multiplication. This works similarly for subtraction, division, and roots, the inverses. Now we have a finished table. Let us see what we can do with it. Take exponential functions, for example. It is easy to see that a represents the y-intercept. When we let x equals 0, b to the x becomes 1, so f of 0 equals a. Also, b is the ratio between the y values at points 1 unit away from each other on the x-axis. In contrast, for linear equations, m, the slope, is the difference between the y values at points 1 unit away from each other on the x-axis. In exponential functions, b is a sort of multiplicative slope. Also, for linear equations, c is the y-intercept. How exactly are these equations related? What happens when we replace each operation in the linear equation with the operation one level farther down in the hierarchy? As you can see, we arrive at the equation for an exponential function, where the y-intercept is the same and the slope becomes the multiplicative slope we discussed earlier. Now isn't that interesting? Although linear and exponential functions might seem very different at first, exponential functions are just one level down in the hierarchy of operations. The motivation of the hierarchy of operations is simply to formalize the connection between things, in this case, linear and exponential functions. Just a side note, it's important to recognize that there can be ambiguity when replacing operations. We don't always know whether we should replace 2a with 2 to the a or a squared. But there's only so many ways it can go, so it's okay to make choices of replacements that lead to where we want. Let's look at one other example. Let's look at arithmetic and geometric series. I don't want to rederive the equations now for the partial sums of arithmetic and geometric series, but they are well known. Here they are. Let's try moving the equation for the arithmetic series down in the hierarchy and see if we land on the other equation. First, it would be good to simplify to remove any ambiguity involving parentheses. It's not exactly consistent how converting with parentheses works, because expanding can yield a different result. D times n minus 1 converts to d to the n if we convert the contents of the parentheses first, because n minus 1 converts to n. But the expanded version, dn minus d, converts to d to the n minus 1. This is another example of the ambiguity I described earlier. Generally, I will simplify out the parentheses to avoid this problem. As a side note, when converting from the arithmetic sequence to the geometric sequence, similarly to how we went from linear to exponential equations, this same problem arises and can be solved the same way, expanding the parentheses. Now that we've simplified, we can finally replace the operations and simplify again. Unfortunately, the result still doesn't match the geometric series equation. What could be the problem now? I'll give you a few seconds to think about it. The answer is, we will not arrive at the partial sum equation for the geometric series. Remember, we have to replace all operations, including the ones between the terms. Replacing operations in the arithmetic series equation will yield the product of the terms of the geometric sequence, not the sum. Instead of a partial sum, we have a partial product. To derive the equation for the partial product, let's write out a few terms of the geometric sequence. Now, let's write the partial products of the sequence. We can see that the exponent for a increases arithmetically in the partial products of the sequence, and that the exponent for r increases geometrically. The exponent for a is n, where n is the number of terms in the partial product. The exponent for r is 1 plus 2 plus 3, and so on, up to n minus 1. This is n times n minus 1 over 2, using Gauss's formula. Putting it all together, the partial product formula is Pn equals a to the n times r to the n times n minus 1 over 2. This turns out to be equal to the arithmetic series equation with replaced operations. That worked out nicely. Moving the arithmetic series and its partial sum formula down in the hierarchy of operations resulted in the partial product of the terms of the geometric sequence and a formula for it. Now that I've shown you the hierarchy of operations, I hope you've gained some insight into the relationship between seemingly separate things in math, or at least in a more formal way. I've thought that this idea of the hierarchy of operations was super fascinating ever since I learned about it, and I'm glad I got to share it with you.